Hey, this is Leach with Simpson Math, and in this video, we will continue our discussion about solving systems of linear equations in two variables. In this video, we'll be looking at solving systems using the elimination, or sometimes referred to as the addition method. So let's get started. So here I have a system of two equations. They are quite simple. We could easily solve this by substitution, no stress. This is more of just an illustrative example about how to do solving by addition or solving by elimination. I will usually refer to it as elimination. So quite literally, just imagine if this was old school addition, like 2 plus 3 equals 5. All right, so same idea, but instead of adding numbers, we're adding equations. So I often like to just draw my equal to bar, my equation bar that we're used to seeing. When you do old school addition, we don't have to write the plus, but I like to put the bar. And then let's just add them. So what is x plus x? Well, that's 2x. What is y plus a negative y? Well, that's actually a 0y. So notice they've canceled, or rather eliminated. How about that? And then 5 plus 11 is 16. So this is a big deal. Right, so these y's have canceled to 0, or they've eliminated. So no more y's. We've added them together, and we now have 2x equals 16. So 2x equals 16, and I can solve by dividing both sides by 2, and we end up with x equaling 8. So I didn't have to go through a bunch of steps with substitution, setting, getting one equal to x and plug into the other. I've just add them up. By y's, divide by 2, x is 8. So then we can do the same back substitution that we're used to. So I'm going to take this and we can plug it into either equation. I just plugged it into the top one. So we get 8 plus y equals 5. Subtract 8 from both sides. 8's cancel on the left, and we have y equals negative 3. So my ordered pair is the solution set of the ordered pairs 8, negative 3. Over here again, if I was to graph it at 8, negative 3, that's my solution. Just a few little technical notes. This 0y that I wrote, you don't have to write 0y going forward. I just wrote it there just to be clear about what's happening. If you want to write 0y, be my guest. Maybe write it lighter or something, but that's not a thing you have to do. All right, so really that's the elimination method. But they're not all going to be just set up so nice and pretty where you can just add and one of them disappears. So let's take a look at this next one. So looking at this example, we have 2x minus 7y equals 2, and 3x plus y equals negative 20. So what would happen if I just added them up like we did in the last one? Well, we get 5x minus 6y equals negative 18. Now, notice nothing eliminated, nothing canceled. We didn't do anything wrong. This actually is another equation that would produce a solution to our system. All three of these are actually going to intersect in the exact same point, but I'm not any closer to figuring out what that point is with this information. So what we can do is I can actually kind of adjust one or both of these, so that way when I do just kind of old school add, one of them will eliminate. So let's take a look at these y's again. Again, anytime you see a coefficient of 1 or negative 1, that's kind of an easy one to usually work with, and that also holds true here with elimination. So what we're going to do is I'm going to take, if I look at these two equations, I'm going to look at the y's, and I notice that if I were to somehow finagle this y to be a positive 7y, then the y's would just eliminate. So how can I do that? I can't just add 7. If I add 7, that's going to affect the negative 20, not the y's. So I would need to multiply. I could multiply the entire equation by 7, right? I could literally just like times 7 and distribute in, and that would work. Well, that's basically what we're going to do. Now, you might have seen a teacher previously do that same sort of exact notation I just did, like throw parentheses around it, do it, and write a 7 like that, and then like distribute. You can think of that that's what we're doing, but for where we are headed In 2 lectures from now, we're going to start talking about matrices. So I'm trying to build some a common language among with us about how to communicate our actions here. So I know it may not be might feel unnecessary, but I'm going to say that this is required. Right? It's required for me. I want to see this notation. So you might be like, what's this R's? So what we're doing is I'm defining the first row as row 1, and we'll just shorthand that to R1. And I'm going to find the second row as row 2 or R2. So we have two equations, and when they, we write equations out, we write them horizontally. So that's row 1 and then row 2 or R1, R2. So what I'm going to do is I'm going to say, well, I'm going to multiply row 2 or the equation in the second row by 7. Right? So it's, oh, I just realized those words are not the right ones. This should be, all right, I fixed that error. So I'm going to multiply row 2 times 7. And again, this is a required notation. So we're going to do just that. So we're going to take 7, multiply them together. So 3x times 7 is 21x. Y times 7 is 7y. And negative 20 times 7 is negative 140. In my years of experience, this step, this multiplying right here, is the step at which most students who know what they're doing would make a mistake. And it's not that they're making a mistake because they made big huge errors. They're just not distributing correctly. Like they'll multiply the 7 well by the x's and the y's, and then they just forget to multiply the constant. Or they will drop that negative or something. Simple, easy, just working too fast errors. So make sure to take your time whenever you do your multiplication. So in this case, just what I would do, honestly, is after you've written it down, then just go back and do just a quick double check. Just go, okay, is 21x 3 times 7? Yep. Is 7y 7 times y? Yep. Is negative 140 7 times the negative 120? Yep. Good. I'm good to go. Let's move on. So don't try to rush through that. Do it once carefully, and then after it's written down, double check that you wrote it correctly, including all negatives. That's the most common error. So take your time when going through there. All right, so now let's add. 2x plus 21x is 23x. The negative 7y plus 7y, that eliminates. It cancels to 0. And then negative 140 plus the 2 is negative 138. Now fear not, when I divide both sides by 23, we end up getting negative 6. Negative 138 divided by 23 is just negative 6. All right, so then we're going to back sub. So I'm going to take my negative 6, and you can plug this into, just like with substitution, either equation. So I'm going to take this negative 6 and plug it into the x. Now, we don't have one where we have already solved for x, or solved for y, rather. So plug it into just to whichever, and then you'll have to do a bit of solving. So 3 times negative 6 is negative 18. Add that to both sides, and we end up with y equals negative 2. Notice I've stopped writing the green notes underneath. If you want to, keep going with the notes, but I've kind of stopped for right now. So we end up with y equals negative 2. So put those together. X is negative 6, y is negative 2, and that's our ordered pair inside of our solution set. All right, let's do this one together. Spoiler alert, it's one of those when we end up with a false or true statement situations. All right, but let's go through the substitution elimination steps. All right, so first up, when you're taking a look at this, that's not set up to just add, right? Look at this. Look at these equal signs. Look at where my y's are. My y's are not on the same side. Back when I talked about substitution, I said, oh, it's a good idea to put them in the form ax plus by equals c. Well, in this case, it's required. You need to put it in the form ax plus by equals c. So here, my top equation's fine. Just copied it down. But now I'm going to add the 10y to both sides. So that I can move that over, and now they're all lined up, ready to add together, right? So make sure that you're clear. It's a good idea to check with spacings, make sure equals are on top of each other, and then x's and then y's and then constants. All right, so now that I have this, let's check about elimination. Now if I just blindly add these together, nothing's going to eliminate. That's not going to work. So I need to finagle this somehow, so that way when I do add them together, one of them eliminates. Now you might be noticing a few things here. So you do need to have, whether you're going to go for your x's or your y's to eliminate, they have to have the same value, the same number. So 5 on top, 5 on bottom, 10 on top, 10 on bottom, x on top, or 2 rather, or whatever. They have to have the same number, but also they have to be opposites of each other. All right. So I'm looking here at my x's. That's the easiest ones to look at. I have this negative. That's good. And this is a positive, so I don't have to worry about the sign issue. So if this was just a negative 5x, then they'd eliminate. So let's do just that. I'm going to multiply this top equation by 5, and then those will eliminate. So I'm going to multiply again row 1 by 5. So I get that 5 times row 1. And then I'm going to be real careful about this. Negative x times 5 is a negative 5x. Negative 2y times 5 is a negative 10y. And negative 4 times 5 is a negative 20. And then do a quick double check to make sure that was right. I didn't change signs. They're all still negative. Yep, okay, good. So I feel good about that. So now let's add. Negative 5x plus 5x, well, that's 0x. And oh, look what happened here. Negative 10y plus 10y, that also eliminates, and we end up with 0y. So on this left-hand side, I just have 0. But on the right-hand side, I get negative 20 plus 8, which is negative 12. Does 0 equal 12? Sorry, rather, does 0 equal negative 12 either? Nope, never, never, never. This is a false statement. So since this is a false statement, we have no solution. So notice these lines are parallel. They both have a slope of a negative half. And if you were to solve both of these equations for y, you would end up with them both being something like y equals negative 1/2 x, but their y-intercepts are going to be different. The blue line would have a y-intercept of 2. The red line has a y-intercept of 1. So they're just barely not equal to each other, but they're never going to equal each other. All right, you have 3 different ways in which you could write the final answer. You could just simply say, no solution. I'm okay with that. These second two both mean the same thing. They're just a different way of writing the same thing. So you know how we've been using these set notation brackets and putting our ordered pair inside? Well, there is no ordered pair that satisfies this. So what if I just erase the ordered pair out, but I kept the set brackets? That's what this next symbol is. This is saying it's the set that's empty. It's the empty set. There's nothing in the set. So just draw the set brackets with nothing in it. Ta-da. This is just a symbol that means the same thing. This is the symbol for the empty set. It's like a 0 or a circle with a line all the way through it going through the other side. So this is the empty set. This is why me as a math teacher, I have students who like to cross their zeros. They pick this up somewhere. To me, I don't like that because oftentimes I read that as the empty set. So if you are a zero crosser, I'm okay with that as long as when you cross your 0, the line stays inside the 0, but that's rather hard to do. So I would probably just stop crossing the 0. The usefulness for 0 crossings is because oftentimes, especially in like typewriter fonts, the 0 and the capital letter O, they look the same. So they just decided to cross the zeros so that way there wouldn't be any confusion between that. But I'm not using capital letter zeros in this math right now, so there's no reason to cross the zeros. So I would probably just not cross the zeros so you don't confuse me and I mark things wrong as the empty set. But the big deal here is we get a false statement, and so we have 3 different ways of writing this solution because it's no solution. So you can write no solution or then either way of writing the empty set. All right, so this next one, I'm going to have you do this one on your own. So you're going to solve this by elimination. Do note, a little hint, make sure to convert it into standard form first. Standard form is the ax plus by equals c. So pause the video and try this one on your own. All right, welcome back. Let's see how you did. All right, so looking at this system here, first I need to put it into standard form. So I do that by adding 3x to the other side. So now I have 3x plus 2y equals 8. And then for my y, my blue one, I also have to subtract the 6y. Almost missed that one. So subtract the 6y. And now it's in standard form. My equals line up, which they did before, but so this is being a little bit deceptive there. So yeah, my equals lined up here, but we had x's and y's all over the place. So make sure you have x's, y's, equal sign, number. Okay, so now that we have that, we need to determine which one is easiest to get to equal the other. This is kind of, the thinking behind this is a little bit like common denominator math. It's at least common multiple, but we have an extra added in thing to think about is making sure that the signs are opposite. So if I was to want to get the x's, if I was to try to eliminate the x's, notice, so just think about if I had some fraction with a fifth, so let's just say 1/5 plus 1/3, what would I have to do to get them to be a common denominator? Well, I would need to multiply the 1/5 times 3 over 3, the 1/3 times 5 over 5, right? So I would have to multiply 3's and 5's on both, right? Well, I would have to do the same thing. I would multiply the top equation by 3, the bottom equation by 5, and actually one of them would have to be negative because they're both positive right now. So it's doable, but not the easiest. Looking at the y's, we have an added benefit of them already having opposite signs, so I don't have to worry about the signs. And then, so what if I was talking about adding 1/6 plus 1/2? Well, if I was to do that, the common denominator is 6, so I just need to multiply the 1/2 times 3 over 3. And then when I do that, I'd be able to add them up. Well, so that's the same thing that's happening here. I can multiply the bottom equation by just 3, and then my y's will be opposites of each other. So let me do that. I'm going to distribute the 3. Again, be real careful when you do. And you end up with 9x plus 6y equals 24. Don't be afraid to double check. All right, then we add. The y's eliminate like we knew they would. We get 14x equals 64. Divide both sides by 14. And we get 64/14, which they are both even, but they don't both have a 4 in. So we can end up with 62/7. Fractions exist. Don't be afraid of them. All right, so we have x equals 32/7. All right, I know you don't want to deal with it, but we're gonna. So let's back sub and put this 32/7 into the x. You can put this into either equation, whichever one looks easiest. So if you had one that had a coefficient of 7, so the 7's would reduce, cool, but we don't. So just put it into this. This one, I think I chose this one because it has smaller coefficients. So I multiplied and I got 96/7, and then I subtract 96/7. And as I mentioned in my in a previous video, don't be afraid of just using side notes. This fraction math is a little bit annoying, but it's easier for me to just do this literally on the side. So say side note, do my fraction math, and I determine that 8 minus 96/7 is a negative 47. And then just do this over here on the side. And so I get that math back. And then dividing by 2 is the same thing as multiplying by half. So since this is a fraction on the right-hand side, and I don't want to write negative 47 divided by 2, I don't want to have to mess with that. I'm going to go ahead and multiply by half. That's the same thing. Multiply both sides by half, so that way I can simplify this. You don't need to have to put a side note over here, but over here is where I did show my pre-reduction. I reduced to 2 out of both the 40 and the 2, and so we're left with, I'm missing my 20 right there, 90, so that should be negative 20 times 1 over 7 times 1. So we end up with y equals negative 27. And so yes, we have those fractions, but that is where they cross. Notice with this one, if I said solve this by graphing, and you were to graph these two lines, you wouldn't be able to very easily know that that was 32 sevenths and negative 20 sevenths, right? So that approximation would be a little bit tricky, but solving by elimination allowed us to get the exact solution. All right, so that's that one. Yes, fractions, they exist. All right, here are two problems. This first one, I want you to practice solving by addition or the elimination method. And then the second one, I'll let you choose. So method of your choice. So pause the video and try both of these on your own. All right, welcome back. Let's see how you did. All right, so when I'm looking at this first equation here, this first system, again, if I can't just add them up, so I'm going to have to do a little bit of finagling. I notice that all four of these, or I do notice first that they are all set up. They're both in the ax plus by equals c form, so don't have to adjust those. They're all positive, so that means that whatever I do, I'm going to have to multiply by a negative at least once. Not at least once. One of them, yeah, I'm going to have to multiply by a negative. So just think about this. So if I had to deal with 1/5 plus a half and get the common denominators, it's multiplying. That's 2 over 2, that's 5 over 5, right? Versus 1/8 plus 1/3, that's 3 over 3 and 8 over 8. So I'm going to have to deal with multiplying both fractions by something to get a common denominator. I might as well pick the numbers that are smaller. So I could do either. So it's the reason why I mentioned common denominators, it's that same exact math, that same exact sort of kind of skip counting least common multiple idea. So it's going to be the same amount of work regardless. I'm going to have to multiply by a negative. I'm going to have to multiply them both by something. So I'm going to attack the x's. So I want to eliminate the x's. So to do that, I'm going to multiply the top equation. I'm talking about the sign in just a sec, but the top equation by 2, bottom equation by 5. And that would then produce both x's being 10 on the other side. So then now I need to deal with the negative because they're both positive. So really, it doesn't matter. I could have chosen to multiply it by 2 and then negative 5 on the bottom, but instead I did a negative 2 on top. Not sure why. I just thought it would maybe easier. Doesn't really matter. So I'm going to multiply top equation by top equation I mean row 1 by negative 2, bottom equation or row 2 by 5. So let's do that math. And I end up with this. Again, be careful with your distribution and then double check once you have it written down. So when I do my x's eliminate, and I'm left with 0x, then negative 16y plus 15y. That's a nice little negative y. Negative 2 plus 10 is a positive 8. So here you can either divide both sides by negative 1 or multiply both sides by negative 1. Does the same thing. You get y equals negative 8. So now that we have our y equals negative 8, now we just need to back substitute. You can pick either one of them. You could actually pick either one of these 4 equations. You can plug them into any of them. I'm going to pick the ones every time that looks like it has those smallest numbers. So I'm going to plug this into the red equation just because it looks like this is a little bit smaller. 3 times negative 8 is negative 24. Then I add the 24 to both sides and we get 26. Divide both sides by 2 and we get x is 13. So put those together and my solution is 13, negative 8. So it's that set of the ordered pair 13, negative 8. All right, lastly, solve this system by a method of your choice. So I chose to do elimination just so you can see it in this form. You could do substitution, but I notice if I just multiplied this bottom equation by negative 2, then I would end up with a positive 2 here. Right? These are both positive, these are both negative, so I'm going to have to swap the signs. So I'm multiplying by a negative. But if this just was multiplied by 2, then it would be the same number, but it needs to be a negative, so the signs swap. So then I distribute and I double check. And then notice we end up with everything canceling. We get 0 equals 0. This is a true statement. So this is an example of when we have a true statement, it's always going to be true. These are actually the same line. Notice that if I was to do 1/2 times R1, I would literally end up with the exact same equation. All right, so they are the same line, not sort of, kind of. They are the same line. And so all that we need to do is we need to say that my solution, it's the set of ordered pairs such that, and then just write one of the equations down. I haven't already solved one for x or y, so it doesn't really matter. All this is saying is this line, which we could graph, but that line, all the points that are on that line, those are all the solutions. And that's what this is saying. All the points on this line are the solution, just in fancy math talk. Again, this is the set of all ordered pairs x and y such that 4x minus 2y equals 2. Or basically, it's all ordered pairs on that line. All of those are my solutions. I hope these 2 videos helped you understand solving systems of linear equations in 2 variables by graphing, substitution, and elimination. And I'll see you in the next video when we're talking about solving systems of linear equations in 3 variables. Take care. I'll see you in the next video.